Alright, we are into chapter 12. So I skipped over sections 5 and 6 in chapter 11. We will go back to section 1 of chapter 12. If you look on your calendars, you'll see that I do sections 1 and 3 together next. But section 2 here is just a little bit different. It's kind of on its own. So I thought we'd start with this one because I did want to make sure I got to this section in particular. And then we jump back into some of the probability stuff. So, permutations and combinations. We're going to go through the differences between these two and how exactly we can use them. But first off, you want to recognize what is a permutation. So we'll get to combination later in the section, but permutation is when a group of objects or people are arranged in a particular order. And the order of the objects is very important. So permutations, if you've talked about this before, you'll remember that permutations is where the order matters. Combinations is where it doesn't matter. So the number of permutations of n distinct objects taken r at a time is given by, and there's a formula down there using factorials that we learned in the last section of chapter 11. So what that means is, for instance, n could be 100 people. And R could be 4, and I want to say out of 100 people in an organization, I need to choose a president, a vice president, a secretary, and a treasurer. And the order matters because you want president to be first, vice president to be second, secretary to be third, and treasurer to be fourth. So you would take 100 objects, 4 at a time, and figure out how many different arrangements of 4 are there within those 100 people. And you could figure out how many different ways we could rearrange 4 people at a time to get 4 officers out of the 100. And it would be a very large number at that point. We're going to reduce that just a little bit to there are 10 finalists in a figure skating competition. How many ways can gold, silver, and bronze medals be awarded? So, what you're looking at doing is we have 10 people, so our n would be 10, and you're taking how many of them at a time? We want gold, silver, and bronze. So we're taking 3 of them at a time. We're figuring out how many different arrangements are there of 3. So we have a permutation of 10 choose 3. So let me say that. And that equals, we have n, which is 10 factorial, divided by 10 minus 3 factorial. Now, you could do this on the calculator. You could do this by hand. 10 factorial, remember, is 10 times 9 times 8 times 7 times 6, 4, 3, 2, 1. 10 minus 3 factorial is 7 factorial. So we have 7 times 6 times 5, 4, 3, 2, 1. Notice this will all cancel with this. So we're really just left with 10 times 9 times 8. Well, 9 times 8 is 72, times 10 is 720 different ways that you could arrange 3 people out of 10. Now, sometimes you'll have objects where some of the things are repeated. So, for instance, we'll talk about, if you look at the next example, we're talking about the word Mississippi, where there are words or letters, repeated. So the way we do that is we just take the total number of objects on top, n factorial still, and then we have, it doesn't matter, there doesn't have to be just 2 things alike, but they just use this for instance. So you'd have p number of objects alike and use that factorial times q number of objects alike, and if you have more than that, then you could continue on using each of those numbers factorial. So let me show you exactly how that works here. So we're looking at the word Mississippi. So we have M-I-S-S-I-S-S-I-P-P-I. M, we have that 1 time. The letter I, we have 1, 2, 3, 4 times. The letter S, we have 1, 2, 3, 4 times. And the letter P, we have twice. So there's 4 different letters. So there's 11 letters. So to find the number of ways that we could arrange this, I guess I'll just use P, is going to be 11 factorial divided by, we have 1 factorial times 4 factorial times 4 factorial times 2 factorial. So you take each of these numbers of things, the different groupings you have of things alike, and those all get multiplied across the bottom. So this one, I wouldn't say to put this, to do this by hand or whatever. I'd say you could do this by calculator. And on your calculator, to find the factorial button, you'll have to go under Math. And if you go under Probability, you'll see there's a little factorial button, or a little factorial key down there. So if you were to do 11 factorial divided by 1 factorial times 4 factorial times 4 factorial times 2 factorial, we end up with 34,650. So there are 34,650 different ways to arrange the letters of Mississippi, in which the order matters. Alright, so let's talk about combinations a little bit. Combinations, very similar to permutations, except the order doesn't matter. So if I go back to that exact same example I gave you before with the 100 people and wanting 4 officers, we would have 100 people, but we would just say we want a leadership committee of 4 people. It doesn't matter which 4, it doesn't matter who's first, it just has to be 4 people. Then what we would say is we would have 100 people choosing 4 of them at a time. So this isn't going to be as specific, which means the numbers aren't going to be as large here. And it's a different formula down at the bottom. At the bottom, the difference here is that on the denominator, we're then multiplying again by r, the number that we're choosing. So let's take a look at an example of what we would do. We'd say a group of 7 students working on a project needs to choose 2 students to present the group's report. How many ways can they choose the 2 students? Well, does it matter how you choose the students or which student comes first or second? It doesn't matter, does it? It matters which 2 students. So here the ordering doesn't matter. So we say we're going to use a combination of 7 students choosing 2 of them. So then we say we have 7 factorial divided by 7 minus 2 factorial times 2 factorial. Well, if we want to kind of look at this the easy way and figure out how to divide it out again, I could write out the numerators factorial times 7 minus 2 is 5 factorial. And then we have 2 times 1. So again, the 5 factorial will cancel out with the last half of this. The 2 will cancel with this and make it a 3. So 7 times 3 give us 21 ways. So again, the numbers here are going to be a lot less than if you had a permutation, because a permutation, the same 2 students give you 2 different orderings. You have student number 1 first and then student number 2, or student number 2 and then student number 1. That's 2 different ways. With a combination, it's going to be a lot less ways. A very common example of a lot of these are using a deck of cards. And especially once we get to probability, you'll see we use a deck of cards a lot. Just because it's standard, and we know there's always a total of 52, and there's 13 of each suit, and 4 different suits, and all that. So it says 5 cards are drawn from a standard deck of cards. How many hands consist of 3 clubs and 2 diamonds? So this is actually going to, we want to determine first, what are we using? Are we using a combination or a permutation? Well, the answer is it doesn't matter which ones are selected first. If you have a 5-card hand in poker or Texas Hold'em or whatever, Doesn't matter which order you draw the cards. It matters what 5 cards you end up with. So our question is, how many hands consist of 3 clubs and 2 diamonds? So it's a combination. But we have several different items here that are kind of happening. So a piece of this kind of depends on what we would have learned in section 12.1 here. But I'm going to kind of introduce it here as we go. So we're going to do 2 different combinations here. We're going to do one combination of choosing 3 clubs, and then another combination of choosing 2 diamonds. So one combination, we have 13 choosing 3. Because we have 13 clubs, and we want any 3 of them. Doesn't matter which order we choose them, but we want to know how many different ways can we choose 3 of those clubs. Okay, so we're kind of isolating the 2 events. So we'd have 13 factorial divided by 13 minus 3 factorial times 3 factorial. And again, you can put combinations in your calculator if you go back to that probability menu under math. So if you hit math, scroll over to probability, you'll see down there where it says NCR. What you do is you hit 13 NCR 3, and it's going to give you that answer. That answer for us is going to be 286. So if there are 286 different ways for us to choose 3 clubs. Then we want to do the same thing for the diamonds. We have 13 diamonds, but we only want 2 of them this time. So then we have 13 factorial all over 13 minus 2 factorial times 2 factorial. And that is going to give us 78 ways to choose those 2 diamonds. Now this is all we've done this section. What they're really kind of depending on you knowing from section 1 is the fact that if you want a total number of ways for the 5 cards, what you do is you multiply these 2 different ways. So then we would take 286, multiply that by 78, and that answer is going to get us 22,308. Different hands. So imagine when you're playing cards, imagine if this is just one particular, you have 3 clubs and 2 diamonds. So imagine if you had now 2 clubs and 3 diamonds, or 1 club and 4 diamonds, or 4 clubs and 1 diamond. There are so many different hands of poker or Texas Hold'em, or whatever you're playing, that you could have out there, that it is just beyond, when you're thinking about those people who play high-stakes poker or any of those things on TV, the amount of odds that are against them and the amount of different things that could be combined out there is really just kind of crazy. So that's just another way of how we can use combinations. So your homework for this section is 11 through 29, the odds, on page 693. And most of this should just be revolved around, a lot of this is going to be word problems, because they're looking at practical ways that you can use combinations and permutations. So your first goal, decide, is it a combination or permutation? Does the order matter or does it not matter? And then decide how to advance and what you're choosing and how many total things you have once you decide combinations versus permutations.